Okay, so welcome to this first lab, and so today's agenda will be uh, a little bit of some of the basics which you might have also looked at in the basic EC lab. So essentially we're going to look into, yeah, thanks a lot. Did the thing. So yeah, as I was mentioning, we will look into the basics of voltage regulator. Then we will move on to switching, and this switching will also include uh, interrupters, which is very useful, and it will include using a transistor as a switch. So I will demonstrate to you various circuits, and we will accordingly discuss. And for now, the grading still hasn't been decided, but I will give you enough home tasks. Most likely there will be an exam. It is not possible to judge almost 150 people. Alright, so make sure you listen very carefully. Whatever will be asked will be something which we would have taught in the class. Alright, so first things first, this thing that you see is known as a multimeter. Let me adjust the. Is this okay? Okay, so this thing is a multimeter. It's a digital multimeter, and right now it's in the off position. So you should always put it in the off position when it is not in use. So it has a variety of functionalities, and the most important functionalities are obtained through the ohm, V ohm and the milliampere, this particular plug. Okay. This is the common, which is the ground, and each multimeter has a specification. So there's Cat 1 600 volts, Cat 2 300 volts. So this particular device can be used for measuring a maximum of 500 volts. Okay, it can be used to measure a maximum of 500 volts. So that's pretty useful. So apart from this, it has a function generator. This particular, if you put the knob over here, it's a function generator. This particular one is to measure continuity and to figure out the direction of a diode, although you don't really need to do that. These two are for AC voltages, 200 volts and 500 volts range. These are the DC voltage ranges, these are the resistance ranges. So it starts from 200 ohms and it goes all the way to 200 mega ohms. But given the fact that this is not a very expensive or reliable multimeter, so the measurements in the mega ohm will be flawed. Then you have the current measuring ones. So for the 10 ampere range, you must swap this particular plug to this. Otherwise, you will blow out the fuse of this particular multimeter. You must swap them out. Okay. So, I mean, most of you might be aware of what this is, but just for completeness, I thought it is prudent to mention. So, for example, let's do some simple measurements.
So what you told in last, sir, like,
Which
like when measuring the current in ampere.
Yeah, so if you want to, so basically if you want to measure currents up to 500 milliampere, then you must use the current setting. So this one is 500 milliampere. Are you able to see the screen?
Yes, sir.
But if you would like to measure something which is like tens of amperes, then you must take out this plug. Someone please highlight it. Someone has to spotlight me. Yeah. So if you use this particular, you must swap this red plug and put it over here. So now it's ready to measure 10 amperes. But this cannot be used to measure anything else. It cannot be used to measure resistance or voltages. This can only be used to measure high amperes. Okay?
Okay, sir. So like for the range of like around 10 ampere, we will plug this on left side.
Yeah. So anything more than 200 milliamps, you must use this particular one.
Okay, sir.
In
Sir,
case of,
the 10 ampere means maximum 10 ampere we can measure, right?
yes, 10 ampere max, after which you will blow out the fuse. If you open this up behind, you will see that, I mean, once you get past the battery, there's a fuse in the motherboard. No, I mean, I wouldn't call it a motherboard, in the circuitry. So that fuse will blow out just to protect the instrument.
And so for measuring resistances, capacitances, you have to use the 10 ampere hole only.
No. For resistances and all, you must use the simple one, this standard one. Okay.
Okay.
I do have a multimeter which measures capacitances and which measures whether a transistor is a NPN. It gives you the key parameters of transistors, the collector emitter base. Um, but I don't have it in my quarter. This is something which I had bought long ago. Okay. So this one is a pretty standard one, and you should be able to get your way with this. You shouldn't have to bother with anything else. So the really good ones are made by Fluke. They are made in the United States. So they are the really high-end multimeters for absolute professionals. The calibration and all is very good. Okay. All right. So without further ado, let's go to some measurements. I have in front of me a very simple circuit. So we will get to the details of this circuit in a while, but yeah, so this is a circuit which consists of a bunch of diodes. It consists of some capacitors. It consists of some aluminum capacitors. Then it consists of a ceramic capacitor. It has one, two, three ICs. It has a resistor. It has a variable resistor. It has some resistors like this. It has some diodes and it has some terminals. So let's say we would like to measure or figure out, most likely I need to bring this forward. So right now I'm in 200 ohms and it says OL, meaning overload, that the range is not appropriate. I mean, is this visible? Is whatever I'm showing, is it visible?
Yes, sir.
Yes, sir.
Sir, if you put the PCB board in the middle, it will be much better. Yeah, it's fine now.
It's not a PCB. Anyway,
Oh, yeah, it's great board.
good. Okay, so before proceeding, good point. So this particular thing, this white thing is known as a breadboard, and it is used for quickly prototyping whatever you want to make. And once you're comfortable with the circuit on a breadboard, you can always go for making a PCB. Okay, so these particular lines, they are continuous. Okay, they are shorted internally up until this middle point. So they are shorted like this up until this middle point. After the middle point, again they are shorted. Whereas for the internal holes, they are all shorted along a certain row. Here they are shorted along this direction, here they are shorted along these rows. Okay, so any doubt what a breadboard is? Yeah, I don't know who is continuously not spotlighting me, but I think I have to do it once and for all. So let me go to settings. I am in settings. Go to meeting options. Yeah. Who can present? Only me. Yeah, so now I should be spotlighting. Yes? Can someone confirm?
Yes, sir. You are spotlight.
Yes, sir.
Yes, sir.
So, yeah, so is this clear how a breadboard works? So these lines are shorted off. Internally they are connected. Similarly, these lines are shorted off, but across this gutter, across this valley, this particular valley, there is no continuity. So in order to have continuity, you must make a bridge like this. You must make a bridge like this. Okay? Or you must make, in order to form a continuity between this and this, you must take a bridge like this. Otherwise it will not work. Should I zoom in more? Just let me know if I should zoom in more.
So for students who
No,
are seeing on laptop, it's fine, I guess.
Okay. On the phone perhaps it's a bit small. Alright, so now let's try to measure the value of this particular resistance. Okay. So right now I am on 200 ohms, and when I connect this, it still says overload, meaning the value of this resistor is more than 200 ohms. Okay, this particular dial should be increased. So I will go to the range of 2000. Now
Sir, can you bring the multimeter in the field of view? It is not actually visible.
it is not visible on the
Yeah.
corner.
So you can
you need
fit
to
the
fit to
frame.
frame.
Visible.
Fit the frame.
So right now what
Okay,
are
yeah,
you able to
thanks.
see on the multimeter?
Yes, sir, it is visible.
So it's 982. So it's basically something like 1 kilo ohm. Okay. This is how simply you measure, and this is how you measure the resistances. So now I'll go to diode mode for these diodes.
Sir,
Yeah,
like there is 20k ohm also, sir. Please, can you show what happens when you switch it to 20k ohm?
yeah, I will show.
Yes, sir.
So it says 0.91. Okay.
Okay, okay.
Now we'll go to continuity. So the when you short whatever you're measuring, it gives an audible buzzer. So you can hear the buzzer like this. Okay. So now what happens when you try to measure or try to figure out whether a diode, I mean, you don't know what direction it conducts. Everyone knows what a diode is, right?
Yes, sir.
Yes, sir.
I mean, you've covered this in basic EC or not? No, I mean, I'm asking for people who have not heard it versus you have been taught it formally. This is my question. Whether you have been taught it formally or you know it out of your own interest. That is my question.
So actually, it is not
Sir,
taught in class.
not completed yet, sir.
Not yet come. So
That
I'll
part.
give you a working idea of what a diode is. Then it will be easy for us. So okay, for now, let me just show you what happens. So right now, if I do this, it gives a beep, meaning there's continuous. Obviously, these two are continuous. Okay, when I do this, the multimeter gives a beep, meaning it's shorted off. So similarly, look, this is a metal. This thing is a metal. So when I do this, you can hear the beep. Okay, it means it is shorted off. This is a metal thing. Okay, so now for this particular diode, if I do this, I hear no beep. If I do this, I hear no beep. But if I do this, I should be able to get a certain value on the multimeter. Okay, when I do the reverse, I get open. Look, on the reverse you have open, right? And on the forward you have a certain value, meaning the red to black is the conducting path. The red to black is the conducting path. Okay, whereas now the red to black is the blocking part. Is that okay? It will only conduct in one direction. It will only conduct from the black to the silver part. If you're able to see clearly, there's a silver ring on the diode. I'm not sure if you're able to see that.
So it's out of focus.
Can you see it now? No?
So no, sir. But like we can
So
see
it's
blur.
It's out
means
of focus.
It's out of focus. Now is it in focus?
Yes, sir.
So here there is a silver ring on this part. On a diode there is a black, it's completely black, and there is a silver ring. So the silver ring is the blocking end, meaning if you apply a voltage from this end to this end, nothing will light up. Okay, this is the non-conducting part that I'm showing, whereas this is the conducting part. Okay, this is the conducting part. So let me give you a brief idea of what. So a diode is represented by this schematically. Are you able to see this?
Yes.
Yes, sir.
And if you look at the actual component, it will look something like this. There will be a ring over here. This will be a silver colored ring. And so you will have conduction only in this direction. Whereas, so if you apply a 5 volt and ground over here, you will have a current in this direction. But if you apply a 5 volt and ground like this will block. Okay, it's said to be in reverse bias. So this is said to be in reverse bias. Whereas this one is said to be in, what do you think this will be called?
Forward bias.
It will be in forward bias. Okay, and so the physics of it, which you should cover in basic EC, or you might have covered, or you will cover, either of the thing. I hope you do cover it. It's basically a junction between a p-type semiconductor and an n-type semiconductor. Okay, that is essentially what it is. All right, and you will see in the basic EC class that how they are created, and it's very, this was one of the path-breaking inventions of the century. All right.
Sir, it was there in CBSE, sir.
It was there in CBSE, very advanced syllabus.
Sir, in main syllabus, I guess, and CBSE board also.
So you have covered in JEE or what?
In JEE mains it was
Yes,
there.
sir. It was there.
Okay.
Yes, sir. The last chapter of physics was semiconductors, and
So you know how diode, I mean, okay, you might have learned about it, but you have not
yes.
seen it in action. That's what I'm getting.
So there, like there is an experiment also in CBSE on this.
Yes.
So in that
Yes,
case,
sir.
you know how diode works. I mean, okay. So for the people who studied the state boards like me, I was not in CBSE. So now you know, Okay, for the people in state boards, various kinds of state boards, now you know. Okay, sabka saath, you have to go with everyone. Alright, so now I've shown you the basics of a multimeter. Now we will move on to some basic measurements on an oscilloscope. Okay, so in order to do that, let me just ready my. Alright, so okay, so this is an oscilloscope. So what does the oscilloscope consist of? Have you done this experiment in basic EC yet?
No, sir.
No, sir.
Come on guys, you just told me the other day that you would have done this in basic EC. Anyway, so it's an opportunity for me to show you. So this is an oscilloscope. Because of space constraint, I cannot put it the way it's supposed to be. This one has two channels. This is called as the first channel, this is called as the second channel. The channels are connected with the help of probes. So these are known as oscilloscope probes. Okay, these are known as oscilloscope probes, and you will see on the probe there is a switch. Is it visible? The switch.
Yes,
Yes,
sir.
sir.
So the switch says X1, X10, and ref. So X1 is for typical measurements where you have no attenuation. So whatever signal you are getting from the circuit is the exact signal that will be shown in the oscilloscope. X10 means it's a 10x attenuation. So if you have 200 volts, then it will drop it down to 20 volts. So it's very useful for measuring higher voltages. Okay, so apart from this, on the oscilloscope, you have several things going on. You have a change of scale.
Sir, a question, sir. Like you said, 200 volts, it will drop down to 20 volts. So is it like the display will be a graph which shows 20 volt? Like,
Yes. But I think in some of the oscilloscopes, there's an option where you can tell the oscilloscope that it's a 10x attenuation, and after that, it will actually account for that drop and show you 200. But even if you don't do that, you should be always aware of whether you are attenuating the signal or just measuring the raw signal. Alright?
yes, sir.
Let me just grab one of my power stick. Facing a bit of a space crunch in my corner. Okay, you have noticed this signal. Okay, so I've switched on the circuit. If you can see, are you able to see these two LEDs glowing?
Yes, sir.
Yes.
Okay, so the circuit's working. So before I proceed to show you the trace, let me just quickly show you what the circuit should be outputting. So I've set my multimeter to voltage measurement and set it to voltage measurement. Okay, 20 volts. So I'm gonna measure what the output voltages are. So this is ground and this is, so here I'm getting 12.09 volts. Is it visible?
Yes, sir.
And between this same ground pin and this point, I'm getting minus 12.5 volts. Okay, So what does it mean when I said all this? It simply means that relative to this point, which is grounded, this point is at plus 12 volts, this point is at minus 12 volts. So this kind of a power supply is very useful to have because it's going from, it's very important for operational amplifiers. So essentially you have plus 12 volts also, you have minus 12 volt also, and you have a ground line also. It's very important to have the ground line plus 12 minus 12. So now I've shown you what the trace looks like, but really, what is the circuit? I've literally plugged it into mains. So this line that you see over here, uh, so this line that I'm holding is literally 220 volts AC. Okay, and this is known as a transformer. So this transformer is having 3 output pins. Are you able to see the 3 output pins? It has 2 input pins and 3 output pins. You have 3 output pins. 1, 2, 3. So why are there 3 output pins? There are 3 output pins because this kind of a transformer is known as a center tap transformer. And in a center tap transformer, you have a step down from 220 volts to 20 volts, ground 20 volts. So now, how do I know it's 20 volts, ground 20 volts? So I should obviously use an oscilloscope to show that. Okay, so I will now try to show it on an oscilloscope. So I'm not sure whether you will be able to, you won't be able, you may be able to see this trace.
Sir, it's AC 20 volt, right?
Yeah, it's going to be AC 20 volts. Correct. So what I'm going to do is, I'm going to use channel 1 only. So channel 2 I'm going to keep on the side. And remember, wherever you are working with mains, you need to be super careful. So let me switch on the oscilloscope. Okay, so we are interested to know how the trace looks like. So this particular probe, this particular kind of probe, it has a ground pin. It has 2 parts. It has a ground pin like this, and it has, can you see this? There's a hook.
Yes, sir.
Yeah, there's a hook. There's a hook. I'm not sure if you can see.
Yes, sir, it can be seen.
It can be seen.
Yes, sir.
Or if you don't really want to use the hook, you can simply take this cap and you can remove it. So you get a point. You can just put the point wherever you want to take the measurement. Okay. So let me, what I can do is I can connect this to the center pin. And now I can probe the other point. So if I touch it on this, so now you see there's a vertical line going, right? Can you see that?
Yes, sir.
But see, of course it's this vertical line, it makes no sense. And that's because the time setting is messed up. There's a time setting here as well. This particular one, it changes the time. So I will go to seconds. And not only that, so it has become more vertical. The trace has become more vertical. So what that means is I need to reduce the voltage range of measurement. So right now it's at whatever volts per division it is, it's too large. So I will go put this down. Okay, and so do you see this sine wave?
Yes, sir.
Yes,
Yes,
sir.
sir.
So I'll just move the trace up. So this particular knob is used to move the trace up and down. Now if you look carefully over here, it shows that the trace has a frequency of 50 Hertz. Are you able to see this? This particular...
So what is the use of center
No,
knob?
sir.
No, sir. Okay, you take my word, it's written here 50 Hertz.
Okay, sir.
Sir, what is the use of central knob?
Central.
So now at second place. Where
Yeah,
Q
knob
is
at second place.
This one?
No, no, at the
right side. On the right side.
yes,
This?
sir, right, sir. Yes, sir.
This one is for the second channel. These are, so I will turn off the second channel. So you see that there's a purple line as well. That is the second channel. So I'll simply switch it off. So there's no more second channel. Okay, it's only the first channel one. So the different components of the oscilloscope are as follows. So let me just attach this cap so that we can just let it go and I can show you. So I will grab hold of this. So now my hands are free. Okay, I have just connected the probe with the help of the hook. Yes, do you get it?
Yes, sir.
So
Yes, sir. Yes.
I'm now free to do whatever. So let's discuss that. What are the different knobs? All the bells and whistles. So uh, this is the first channel. If you want, someone can take a screenshot of this. So this is the first channel. You connect the multimeter probe over here. This one, this particular knob and this particular knob belong to the first channel. They belong exclusively to the first channel, right? This particular knob and this particular knob, they belong to the second channel. All right. This particular knob is for the time division. So right now, if you look at the oscilloscope, now if I just move this to seconds place, you will see that it has more trace. It has more trace per division of the oscilloscope. The oscilloscope screen is split into divisions. So per division, it has more traces because I am plotting more per division. Okay, more seconds per division. So in order to make it better, I will reduce it. I will make it something like this. Okay. Okay. So now I have more buttons over here, which you may not be finding it very useful right now, but eventually if you go into this area of work, you have cursors, you have measure, you have acquire, save, then you have a single measurement. So right now we are doing a continuous measurement, but you can also do a single measurement. So for example, a single impulse or a single pulse measurement you want to do. So for that, in order to tell the oscilloscope that okay, now you need to start measuring the signal, there is an entire set of triggers. So an oscilloscope can be triggered. So there are various kinds of triggers. So there's a rising trigger, there's a falling trigger, and we will discuss this towards the end of today's class. See, because I need to manage in this space, so it's not possible for me to whip out my notebook right now, because I might get shocked because I am also crunched for space in very close to 220 veins. I mean, I have put some glue gun over it, so it's insulated, but I don't want to risk it. So where was I? Yeah. So now you have this particular circuit, which has the input as a full sine wave, right? You have the input
Hello,
as a
sir.
yeah.
Sir, if we will put the probe on the other side,
Hmm.
will the wave will be same?
It will be out of phase. Let me show you. So I have another probe. I will switch on channel 2. I switched on channel 2. So now I will take this See, can you see the other trace?
Yes, sir.
So they are out of phase. I hope you appreciate this, man. They are out of phase by 180 degrees. Can you
Yes,
see?
sir.
So I'm using
Yes.
both the probes simultaneously right now.
So where is the third probe coming from? Like, is it attached from
It's
the
common ground.
oscilloscope?
It's common ground. So this, I don't need to attach this. It's common ground. Internally they are all shorted.
Okay.
Unless I specifically connect this. So I can move this trace independently as well. I can make it larger, I can make it smaller, I can make it larger, no problem. I can make it larger, then I can switch on my attenuator. I can attenuate the signal. I have put it on 10x, so it will be much smaller compared to the when you see the effects of attenuating, it's a bit distorted. Okay. I'll go back to the normal.
So what is the use of that USB input in the oscilloscope?
You can actually save the traces. Can actually save the traces. So there was once an experiment, a very simple experiment. I just wanted to prove a point to someone. So I took a piezoelectric disc and I took a long channel of aluminum. So I stuck the piezoelectric disc to the bottom and top part of the aluminum, and then I hammered one end with the help of a big hammer. So there was a traveling wave. So the traveling wave caused changes in the voltage output of the piezometric disc. So we were able to measure it with the help of this oscilloscope. We were able to save the trace, and knowing the time divisions and all, we were able to pretty accurately figure out the speed of sound in aluminum. Okay, that was pretty close to the theoretical value. So that's where this USB is important. You can save. So there's a button over here: save, recall, acquire. So you can save. Okay, it's out of. So there's a save button over here. This button saves the trace. Okay.
Okay, sir.
So let me get rid of the trace.
So what is the use of the third channel?
That's not a channel. That's an external trigger. If you want to start acquiring a certain signal, once a certain something happens, maybe it's coupled to a camera or a sound sensor or whatever. So that's an external trigger.
Okay.
Okay, so now we get to the first part finally, which is how to get this kind of a power output, voltage output. So you have this kind of a very simple circuit where you're drawing power from mains. So you're drawing power from mains, and then you are rectifying it and eventually getting a stable 12 volt DC, 0 volts, minus 12 volts DC, and a variable output from all this. Okay, so the question is, I mean, why is this important? Because in many applications you want a very fixed output in order for various ICs or various components to function. So these two components are known as voltage regulators. Okay, so they help in providing regulated output like we had seen. And regulated output means even if the incoming voltage is fluctuating or changing or whatever it is, despite that this output will be remarkably stable. So there are various conditions under which this holds true, but essentially this is what it is. It tries to hold the output to a certain level regardless of what is going on. So these kind of things are called as regulated output. So have you heard of the term regulation of a transformer? In your first year you might have studied this in electrical. So for a transformer under no load you will see a certain voltage. When you start loading the transformer, then the voltage at the output of the transformer also starts to reduce. You've heard of this, whatever I just said?
No, sir.
Okay. Okay, I mean whatever I just said that happens, and so in order to avoid that you do that. So what are the different components? Let us quickly discuss what are the different components. So you have a transformer, then this particular section, okay, this particular uh, collection of 4 diodes. So there are two different circuits over here. One is getting a 12 volts and minus 12 volts output, and one is to get a variable output. So we will discuss them parallelly, or rather we will discuss them one by one. So let us first discuss the 12 volt output circuit. So this particular arrangement of diodes is known as a full bridge rectifier. I'm sure you might have seen on YouTube, there is one channel called as Electro Boom, who really emphasizes on the full bridge rectifiers for no apparent reason, but yeah, it's a very entertaining channel. So this is that full bridge rectifier. You have seen it in action today. This is a full bridge rectifier. Then the full bridge rectifier goes into a set of filter capacitors, and we will see that. We will see the traces, what happens when you remove the capacitors, when you leave the capacitors on. We will see that. And finally the output after filtering is going into two different ICs. One of the ICs, it's called a 7812. It's a LM7812 voltage regulator IC. There's another IC which is called as LM7912, which is also a voltage regulator, but also inverts the voltage, meaning it gives you a minus 12 volts. Well, it doesn't really invert, but yeah, it takes negative voltage in, and with respect to a certain ground, we will see that when I will show the schematic, and then it will output minus 12 volts. And we have given two indicator lamps, so these two LEDs are just to indicate whether we are getting power or not. So this is briefly the circuit. So you have different sections. First is the rectifier section, then you have a filter section, then you have a regulator section, then you have finally the output. And I have already shown you with the help of a multimeter what the output is gonna be. So before going into the circuit, so let me just show you certain waveforms. So I'm gonna switch off channel 2. You're just gonna need channel 1 for this particular so I'm gonna put channel 2. I'm gonna put it over here. I'm just gonna put channel 2 over here. Okay. Okay, so when I connect it like this, you get a flat trace, meaning the output is DC, but okay, the trace is lost. Pardon me. Yeah. So this is the distorted sine wave that you get with respect to. So let me just remove the filters and show you what happens. Just a moment. Yeah, so let me just remove the two filters. So here you see full bridge rectification on this screen. So this particular waveform is known as the full bridge rectification. Is it okay? See over here you have the cusp, so it's not going to the negative side anymore. It's simply bouncing off. Okay.
So where is this probe connected?
It's
Which
gonna.
hole it has been filled?
Pardon me.
So in which hole it has been pressed?
It's holding one. Okay. So I think in order to discuss all this, first I need to. It is better to discuss the schematic first. Otherwise, nothing will make sense. So they have polarities. I have to really look into how to just put it in. Okay. So yeah. So let me switch everything off. Let me whip out my notebook, and then we can first discuss the schematic, and then we will again start the probing. Otherwise, it will not be easy for you to understand what exactly is going on. But everyone has heard about what a full bridge rectifier is, right? Like you studied it in some
Yes.
class.
Yes.
Like officially you studied it, right? Or it's some unofficial thing that you're talking about. You studied it officially? Or not?
No, sir.
No, sir.
Okay. I'll just give you a brief working idea of that. So now we are looking into full bridge rectifier. Okay. So we're gonna deal with a full bridge rectifier. Is this visible even? No?
Sir,
No,
the
sir.
light.
The lighting is
No, sir.
Yes.
Reflecting off.
too
Yes, sir.
bright.
Light.
Now?
Partial it is visible.
Now
Like
it is visible.
Sir, but it is blur.
Sir, if you can dim the light a little bit more, maybe then.
I cannot dim the light.
yes, sir. Now it's visible little bit.
Yes,
Yes, sir.
yes,
Now it's
after.
visible.
Yes, sir.
Basically, okay. Everyone's struggling with their throats. So you have essentially a rectifier, a transformer like this. A center tap transformer, we've already seen the trace how it looks like. Okay, so you have something like this. You have 230 volts, 50 hertz input. You have an output. So in this particular case, it's 20, 0, 20. So this 0 volt line is what we say our 0 volt line. No problem. It's the center tap. Alright. So now between these two, I've already shown. If you connect these two and these two, you get two opposite phases. So basically, if you were to probe between this point and this point, you would get a AC output of swinging from what, minus 20 to plus 20. This is what you would get, or rather you would get a 40 volt swing. All right. So now what happens is, if you want to convert it into DC, so full bridge rectifier is a way to convert an AC signal into a DC signal. So let us first see what happens when you just use a single rectifier. So say I have a AC source and I connect it to a rectifier like this. So over here I have a AC signal. So if I were to then probe it with the help of an oscilloscope, I would have a signal like this coming in. Now I already mentioned to you that a diode is going to allow a forward bias like this, whereas a reverse bias like this, it's not going to allow. So when the voltage with respect to this point, suppose this is grounded, so with respect to this point, if this is at a higher voltage, we say that the diode is under forward biasing, otherwise we say it's under reverse biasing, right? So under this situation, what will happen? For half of the wave, this point is more positive with respect to this point, so it will allow the current to pass. So you get a, so this particular point will eventually be at this voltage. I mean, this, suppose a resistor going to ground. So if this diode is in forward bias, then you have a conducting path. Essentially this becomes short circuited, so the voltage at this point becomes the same as voltage at this point. So you follow this. I mean, of course there will be some non-idealities, but you more or less follow this. Now at this point the voltage goes below the 0 volt, so this diode becomes in reverse bias, so the voltage will go like this. Then again it will be like this, then this, then this. So this particular thing is known as a half bridge rectification. Okay, this particular thing is known as a half bridge rectification. In order to get, so what's happening? I mean, half of the wave you're actually clipping out. Half of the wave you're actually clipping out, so you get, I mean, only half the power output. So in order to avoid this, suppose the output is this, so you have some AC signal coming out like this, and you would like to really get a full wave rectification, so you feed it into what is known as a full bridge rectifier. So it comprises of 4 diodes arranged in this particular configuration. Okay, and the outputs are taken from this point and this point. Okay, so what happens in this case is, the original waveform is like this, and because of this rectification, now you have rectifications on both cycles. So if the output is something like this. Okay, so this particular output, this particular waveform is known as a fully rectified waveform, and this particular arrangement of diodes is known as a full bridge rectifier. Full bridge rectifier. Okay, but because it's such an important sort of component of many power supplies, it directly can purchase what is known as a rectifier unit. So the rectifier unit has 4 legs, and on top of the rectifier you will see 2 legs which are marked with this AC symbol, and one of them will be positive, one of them will be negative. So you simply connect the AC signals or AC voltage to these 2 particular points. It doesn't matter how you do it, and you will get a positive voltage over here and a negative, I mean not negative, but relative to this point, so this can be considered to be ground, so you will get a voltage over here. Okay, so this kind of units you can readily buy. I did not have them at hand for putting it to this circuit, so I simply made it from 4 circuits. Now, a very important thing about these diodes. So over here I am using what is known as the 1N4007 diode. So the part number is this 1N4007, and every diode has a forward voltage drop, meaning suppose you were to apply 5 volts over here, and there's a resistance and it goes to ground. So the moment you have a forward conduction across this diode, you will lose some voltage. So that is known as the forward voltage drop. Forward voltage drop. Typically that is 0.7 volts for this particular mode. For heavy duty diodes it will be even larger. So you will get over here 4.3 volts. Okay, so you must factor this always when you are designing circuits with the help of diodes. Alright, so now getting back at the original.
Sir,
Yeah.
so is this voltage drop because of the inbuilt voltage of the diode?
I could not get you.
Is this voltage drop because of the inbuilt voltage of the diode?
The voltage drop is for?
Is because of the inbuilt voltage of the diode.
No, there is nothing called as the inbuilt voltage per se, but it's because of the junction properties between the P junction and the N junction.
So the barrier potential?
Yes, it is the barrier potential. Correct. Okay, so where was I? Yeah. So now you pass it on to the full bridge rectifier over here. So I'm just gonna do it as a block diagram. So the output is gonna be 20, 0, minus 20. Okay, the output is gonna be 20, 0, minus 20, because this is a center tap transformer. You have literally the 0 volt reference as well. If you were not to be using a center tap transformer, this would become 0 and this would become 40. Okay, alright. So after the full bridge rectifier, you have this kind of a signal. Okay, it's just bouncing with respect to the 0 line. So it means that the voltage does go to 0, then again it rises, then goes to 0, again it rises, then goes to 0. Okay, so at this point, what is the frequency of this wave? What is the frequency of this wave?
Double.
It should be double, right? So we should be able to see that doubling business in the oscilloscope as well. So let's see. You get the point, right? It should be double. So I'm a bit worried about this capacitor, but it's a bit swollen. So of course I'm not gonna. It's not gonna. I mean, it does fail catastrophically, but it's not so dangerous as you think it is. So we have not yet put the filter capacitors in the circuit diagram. So What I'm gonna do is I'm gonna remove the filter capacitors. I'm gonna remove the filter capacitors. There we go. So now I'm gonna probe at the exit of the full bridge rectifier. I'm gonna probe them. Okay, so I'm gonna probe between these 2 points. Basically the output of the rectifier, so I should get this kind of waveform. You can smell it. Okay, so this circuit is busted. Okay. So that's this particular diode is busted for some reason. I could smell the magic smoke. So just you have to bear with me on this one. I already burnt my fingers. You see. So something has happened because of which I think when I was putting the capacitors back the previous time, I changed the polarity. So this particular thing is busted. So anyway, I mean we cannot use this particular rail anymore. So I'm just gonna remove the voltage. I don't have a voltage regulator spare at this point. Hello?
Yes, sir. Sir, is it hot because it is an heat sink?
Yeah, so I will tell you how to do those calculations in a while. But let me just now grab hold of something to remove the that one's tongue. Let it just become cold and then we can remove this. Yeah. So this one has gone. And this does happen. I mean whenever you're making analog circuits and all, so this kind of things do happen, and there's nothing to be really worried about except that thing is damn hot. Just a moment. Let me just. Never mind. We have another set of. We have another rectifier unit over here, so we can discuss with this. So the polarity of these capacitors really matters a lot. Otherwise, you get this kind of things happening. Hopefully, this was not. This wasn't hot. Yeah. So this magic smoke business, it will happen to you. It will happen to the best. I'm not saying I'm the best, but it will happen at some point of your life. Okay, no worries. So let us restart. Yeah. So yeah. So let me just remove this filter capacitor. So I've removed the filter capacitor, and I'm gonna probe the outlets. So here the outlet is from this to this. Okay, so right now you have the full bridge rectifier over here. You see the full bridge rectifier. So the Vmax says 61 volts. So what we can do is we can always measure. So I'm gonna go to measure voltage. No, I'm not gonna go to measure. I'm gonna go to cursors. Cursor A. Oops, sorry. Cursor A. Where is it? Cursor A.
Sir, the graph which is forming on the oscilloscope, like it is curvy on the top, but like it is pointed in the bottom part of the curve. So why is it
Correct.
so?
It's because of this. I mean, it's like this sine wave, it literally gets reflected. So you get a cusp over here. You're correct. I mean, that is how it should be. If you just
Yeah.
take the negative part of the sine wave and just flip them, you will, this is exactly what you will get. Okay. So if you, I don't know
Uh,
whether you can see the frequency over here as well.
but sir, like the pointed part, which is in the below of the curve, it should it should be above the x-axis, but it isn't.
No, so I can shift the origin. So
Okay, okay, okay.
don't worry about that. So that you should not look into. Okay, so the frequency of the wave. For some reason, I'm not able to find the two cursors. Weird. So can you look over here? Are you able to read this part?
No, sir.
Okay, it says
Sir,
100.
it's blurred.
Basically, it says 100 hertz. Okay.
Okay, sir.
So what that means is right now this wave is at a frequency of 100 hertz. So now I'm gonna carefully take the filter capacitor, and then now without making that particular error, I'm gonna put this filter capacitor in. So which one is it? So this is the negative part. This is
So
gonna be,
before putting it, can you tell like how you are putting in a sense like what strategy you're saying? Like what should we put where?
okay. So this is the negative end of the electrolytic capacitor, and obviously this is the positive end. So for the negative rails, whatever is going to be grounded, this is to go there. So in the circuit, in this particular circuit, this black rail is the ground rail, and so it's like saying the minus 20 is like the ground rail. Or if you want to just look at between 20 and 0, the 0 is going to be the ground rail and 20 is the positive rail.
Okay,
So
got it, sir.
so this negative should go into the 0 and positive should go into the 20, not the other way around. If you do the other way around, you get nice burnt fingers. So yeah, I'm gonna carefully put this over here.
So there is usually heatsink attached to that regulator, right?
Uh, yeah, I mean, you if you know you're gonna dissipate a lot of heat, then you can put it. Otherwise, it's not necessary. Okay, so did you observe the change in the waveform? I'm just gonna bring the waveform down a bit. What do you see now? So I'm gonna just remove the filter capacitor again. So when you remove the filter capacitor, it is this, right? Now when I put the filter, this is what you get. Do you see?
Yes,
Yes,
sir.
amplitude
Converting
change.
to DC.
Yeah. So it's simply filtering everything and it's getting converted into DC. So I mean, if you were to plot it, like this, it's literally just going on top of these peaks, and it's sort of holding it at that value. Okay.
Sir, is it making the transient circuit?
Yeah, it is making the transient circuit essentially.
Okay.
Okay.
Thanks.
So yeah, before I do that. Yeah, this is also going out of regulation.
So is there any reason for there being a asymmetric nature to what it has done?
Yes, there is a reason, because after the voltage reaches the peak, the the waveform starts to dip, and the capacitor is trying to make up for. So it's like the RC decay that is happening. This is the RC decay part, okay, and this is the RC rise part. So it's just RC circuits going on.
Okay.
Okay. Okay. So yeah. So now you know how a filtered circuit looks like after a full bridge rectifier. So in many cases I mean, you don't bother with the rectifier, you will just get the voltage just going very close to zero. But if you don't want that to happen, if you want the voltage to just stay in this region, then you will use a filter capacitor. Okay? And remember, this kind of aluminum capacitors, you really need to keep an eye on the negative and the positive point. Okay, you don't want popping capacitors all over the place. And it's still pretty warm, this thing. So this thing is busted. So this is how a voltage regulator looks like. And so because it's busted, all I need to do is I just need to take a new one. I just put a filter capacitor here, and I will just get it working again. So nothing for me to worry about. Okay, so that was okay. So this capacitor also gone. So I was telling you it's a bit swollen. So I've
So
used
this is
very
smoke coming.
yeah, there's some magic smoke. So that the reason was this capacitor was swollen from the get-go. Okay, capacitor was swollen from the get-go, so it simply went kaput. So this kind of things do happen. I mean, these are very old capacitors that were lying around. I did not bother buying a new one. There's nothing to be very worried about. Simply remove the circuit in question. And aluminum capacitors are very dubious in this sense. I will send you some video links, you can have a look at them later. Okay, so let me just...
So can you make a spark like electro boom?
No, I don't. I have done several of those in my lab, but now is not the right time. Okay, so we've got rid of that. So right now we have LM317 circuit. So anyway, I'll just show you the schematics of the circuit. I didn't think I'd be covering all this, but yeah. So let me turn off the oscilloscope. We don't have anything to do with the oscilloscope right now. So let me just get rid of this. I need some space on the table. There are many more, I mean not many more, but there are some more circuits I would like to show you, but let me just get rid of the scopes. So where was I? Yeah. Voltage regulators. Right. Anything. So there are various kinds of common voltage regulators, and there are two kinds of, I mean not two kinds, there are various kinds of regulators, but the one where we have used what is known as LM78XX, and we have also used the LM79XX. So these are known as linear regulators.
The screen is not visible, sir.
No.
Whatever is written.
Yes, sir. Now it's visible.
Now it's visible, sir.
Okay, okay. So maybe I need to how to make this work. No?
Yes, sir, it is visible.
Yes, sir. It's visible.
But I cannot write like this. This is not visible, right?
Sir, it's visible, sir.
It's visible, sir.
Now it's visible, sir.
Okay. So you have this kind of regulators. They are known as the 78XX and 79XX. So by XX, the last two digits tell you what the regulator is going to hold it at. So 7805 and 7905. So 7805 is going to give you a 5-volt regulated output. 7905 is going to give you a 5-volt regulated output. So 79 gives you the negative voltage and 78 gives you the positive voltage. Okay. So now what's a linear regulator? I mean, so a linear regulator, I mean, functionally what it does is you have some voltage input, and the regulator, so it's rated for suppose 5 volts. So it's gonna hold at 5 volts regardless of what this V input is going to be. So V output is going to be 5 volts. This is what you desire. And V in this particular case, I mean, it could be anything, but in this particular case, because they are linear regulators, uh, they are not switched regulators. No need to know what these are. But this V in has to be larger than what your V out is. So the V in has to be definitely more than 5 volts in this particular case. Okay, so if you desire a 5 volt output, you must give V in which is larger than V out. And the difference between V in and V out, so V in minus V out, is known as the dropout voltage. So the typical dropout voltage is going to be 2 volts for this kind of 78XX. So let me see if I can show you how the datasheet looks like. So let me share my screen. Is my screen visible?
Yes, sir.
Let's just go to the 7805 datasheet. So you see over here, you have a datasheet for the 7805 series, and this kind of a package, it's okay, you cannot see. So the package that you saw, it's called as a TO220 package. Okay, it's called as a TO220 package, and you also have surface mounted packages which look like this. So if you look at the data, I mean, this is what the internals of the circuit looks like. Okay, so don't worry about that unless you are really into analog electronics. There is one guy from electrical who was also auditing the course, so for maybe for that guy it's important. Okay, so if you look at the input voltages, so the minimum input voltage has to be 7 volts. Are you able to see this?
Yes, sir.
So the minimum input voltage has to be 7 volts and the maximum can go to 25, but you should not operate at 25 volts in order to drop it down to 5 volts. So this is for 7805. So in order to get 5 volt output, the minimum you have to give is 7 volts. So what is the dropout voltage? The dropout voltage is going to be 7 minus 5. Okay. Now if you look at 7824, so what is the dropout voltage for the 7824 IC?
3 volts.
3 volts.
3 volts. Very good. And so what is the output current? It says 1.5 ampere, right? So now let us figure out what is the power that is going to be dissipated. So you have an input, you have an output. So the input is going to be say 7 volts, right? The input is going to be 7 volts and the output is 5 volts, and the maximum current that it can transfer is 1.5 ampere. So the power dissipated by this package is going to be V in minus V out times the current. And in this particular case, what is the V in minus V out? It's going to be 2 volts and the current is 1.5 ampere. It gives you a value of 3 watts. So this is the minimum power that's going to be dissipated. I mean, it's not going to be the minimum. It's like the minimum power dissipated at maximum amperes. The minimum power can be very low. If you're drawing very less amount of amperes, if you're drawing less amperes, obviously this power dissipated will also be less. But this is like you're working at the dropout values. Okay, but now you saw that the input voltage can go as high as 25 volts. You are not in the dropout region, you are much above the dropout region, so it's going to give you a 5 volt output. So in that case, what is the power dissipated? It's going to be 25 volts minus 5 volts times the current. So what's it going to be? 20 times 1.5, so it's going to be 30 watts. That's a lot of power. 30 watts is a lot of power. Okay, and now the temperature is going to rise really quickly. The temperature is going to rise really quickly, and let me just see in the data sheet if they have given the so typically they will also give you the thermal properties of such kinds of devices, because the designer must know whether you need a heatsink or not. It's not always convenient to give a heatsink. I mean, just because you feel like it, you should not give a heatsink. You should do the calculation. So anyway, we don't have in the data sheets provided by Texas Instruments. I'm not able to find that particular the thermal characteristics. Okay. Temperature coefficient, no. Okay, I don't see it in the data sheet. But you should be then be able to find out the steady state temperature of this unit. Okay, so this is about the linear regulator. So the overall circuit, so you have 20 0 minus 20, and then you have a filter capacitor. Okay, you're not let me in fact switch to my, so now if I switch to my tablet, then I need to have another thing on my table, so I don't have so much space for that. Maybe if I switch off this light, does it make things better? I don't know. Is it better?
Yes, sir, it's fine.
Light is better.
Yes, sir, it's fine.
Okay, so now you have the 0 volt line running like this. Okay, you have the 0 volt line running like this. You have the minus 20 volt output over here, so you're gonna pass it to this 79XX, and over here you will pass it through the 78XX. So let me just draw the schematic first, and we will look at how the pinout looks like. So you have one input going into the 78XX and one input going to 79XX. One input is directly connected to the ground reference line. Okay. So the third line is going to be the output. So you give another coupling capacitor. This is not strictly required, but these are required. Okay, because the input line has to be filtered before going into the. Why does the input line have to be filtered? Why does this capacitor, which is the output of the full bridge rectifier, so this is the full bridge rectifier. So why does the output of the full bridge rectifier have to be filtered? You know, when you want regulated output.
So to get a relatively steady rate of voltage.
Well, yes. I mean, first of all, you need to get a relatively steady output, but there is something else.
So the minimum, like the voltage will drop below 7 volts.
Very good, very good. So that is the precise answer. If we do not use these filter capacitors, the voltage will will go into the dropout region, and we will not get regulation anymore. We need to always be above V in minus V out should be larger than the dropout voltage. In this case, it should be something around 2 volts to 3 volts. Okay. Everyone, is it clear?
Yes, sir.
So then the output still, I mean, the output capacitor is there so that even when you connect a very heavy load, it doesn't fluctuate a lot. And finally, you can connect it to load. So you get 0, XX and minus XX. So this is how simple voltage regulator circuit looks like. Okay. This is how a simple voltage regulator circuit looks like. Alright, so now let us go to the adjustable voltage regulator. So there is a very, so I'm just telling you the famous components because anytime you want to build anything pertaining to analog electronics, I mean, this is just the starting point. I mean, if you want to make some kind of thing which draws power, of course you need to first make the power supply. You cannot say that, okay, I don't have a power supply, I don't know what to do. No, you need to be aware of all this. And we spent a bit of time because I mean, many of you were not aware of such kind of things, so it is worth spending a bit of time rather than rushing through everything. So then the second popular IC is known as the LM317. Okay, the LM317 is an adjustable output. It's an adjustable voltage output IC. So once again, it's a very simple IC, LM317, and again it looks very much the same. If you look at this is the LM317. Okay, and this is known as the LM317. Nothing hot about it. So the LM317, once again, it has a ceramic filter capacitor at the input. So you have the in, so you have a ceramic capacitor like this, and you then have an output, but now the output you need to create a voltage reference voltage divider for the reference. Okay, this is very important, otherwise it doesn't work. You need to create that voltage divider. So let me just draw the schematic real quick. So this is going to be the output line. This is the output line, and you need to create a voltage divider between these two pins. So the LM317 obviously has 3 pins. One is the input line, one is the output line, and one is the adjust line. So this line is called as the adjust. And in the adjust line, there is one resistor which is connected between the V out and the adjust, and another variable resistor connected to this. So if you measure the resistance from here, you get a variable resistance to ground. Okay, so in this particular circuit that I have drawn over here, this one is 5 1000 ohms and this is 270 ohms. So this is 270 ohm. I'm not sure if so this is 270 ohm and this is 5000 ohm. But the 5000 ohm is between this point and this point. This is completely 5000. But you know that any potentiometer, like a variable resistance, it has three legs. Let me have a spare line around in my hand. Yeah, so they look something like this. Okay, can you see this?
Yes, sir.
So they basically have three legs, one leg, two leg, three leg. Okay, so if you measure the resistance between this leg and this leg, you get, so this one is how much? This one is 105, so it's 10 kilo ohms. So I can show that to you on a multimeter as well. So I'm gonna set the range to 20. I'm just gonna okay, it's still overload. Okay. Okay, so it's 1 mega ohm. Okay, it's 1 mega ohm. And if I use the middle leg to now measure the resistance, it will be something less than 1 mega ohm. So right now it's 0.48. So how do I change the resistance? How do I change the resistance between the two legs? I just need to rotate this screw. Can you see? There's a
Yes.
screw over here. Yeah. So I just need to rotate this screw, it will change the resistance. So similarly, over here, you have a 5k resistance, and by changing the screw, you're essentially moving this point up and down. So you can go anywhere from 0 ohms to 5 kilo ohms, no problem. Okay, and you can see that over here. This is the trim pot. It's called the trimmer pot. So it's going from 0 to 5k if I rotate this screw. Okay. And finally, this is the output. So the output is given by 1.25 times 1 plus R2 by R1. And this one is R2 and this one is R1. And this is how you figure out what the output is gonna be for the adjustable voltage source. Okay, so the recording is there. We have covered a bunch of different topics starting from multimeter. We've gone from multimeter to oscilloscope to full bridge rectifier, half bridge rectifier, filtering, going into a voltage regulator. We have looked into 780, 7812, 7912. I mean, I was using 7812 and 7912. Then we have looked at 7 LM317. We've looked at what uh, voltage dropout is. We've looked at what resistance, what the forward drop of a diode is. Okay, we've looked at many concepts. So keep everything in mind. So after a 5-minute break, we will look into how to use a transistor as a switch, and we will see some very important concepts of switching, including an opto-interrupter, and we will see how relays work. So all this coming out after a 5-minute break. Okay, don't go anywhere. A lot of fantastic things to come. I mean, at least things which I find fantastic. I hope you are enjoying this. I don't know. I'm not getting very clear signals. No pun intended. I'm not getting a very rectified signal from you guys. So let me just stop recording for the moment. We will join after 5 minutes.